Thank you. Go ahead.
Okay, so good afternoon, and I'm here to present. So my name is Sheldon Williamson. I'm a professor and a Canada Research Chair up at Ontario Tech University in Oshawa. The work we've been doing over the past 15 plus years is on electrified transportation. The work I'm presenting specifically to you today is an up-and-coming technology in universal onboard EV charging. And by universal, I mean onboard chargers do exist for electric vehicles today. As you can see in my picture here that I'm showing you, the charger actually sits on board the vehicle, hence the name onboard charger. Basically, what happens is it takes it from an AC charging station, it goes onto a vehicle in the form of a plug. The onboard charger, or the OBC, sits on top of the vehicle and then charges the electric battery, or the battery pack of the electric vehicle. However, what has happened in the recent years is that battery voltages have not been standardized. So commercially available onboard chargers today, they have a wide range of output voltage, depending on the type of battery they're trying to charge. So it's tailored for a specific voltage. And what we are trying to propose here, so you can see here in this picture, there are different, of course, there are a plethora of chargers to choose from, but with different voltages. So we are proposing the market advantage of our solution would be one size fits all charger topology, which basically encapsulates all these varied battery voltages. So we've tested for voltages as low as 50 volts and as high as 450 volts. The advantage is also that it uses a very simple controller, so it's very cheaper to produce. And as I said earlier, because of the wide voltage range, there's a lot of modularity in the design. Right now, we see the market growth by 2030 to be close to $15 billion market for electric vehicle chargers. And with the adoption of EVs even faster, I can see this growth rate even going further up by 2030. As I said, we tested on a Toyota Golf cart, which is in the range of 48 to 72 volt battery pack. The same charger on a megawatt electric vehicle, which is a small size electric vehicle, from about 72 to 150 volts battery pack, and finally from 200 to 450 volt battery pack. The other thing I should mention is also it is agnostic, or it's independent of the chemistry that the battery uses on board the electric vehicle, because there are several types of lithium batteries, whether they're lithium ion, lithium polymer, or any other solid state batteries which are up and coming. We've tested our chargers on those. We've got interest from two of the top eight charger companies in the form of Brusa and Ficosa. They were very interested in our patent, which was filed up in 2018, back in 2018, and Allah was instrumental in that. We've also garnered recent interest from Ford. So we have an actual OEM on board willing to test our charger for their up-and-coming EV fleet. So the advantages of the technology itself, first and foremost, is that it has the universal charging voltage. So our output voltage range between 50 and 1000 volts. Now you would say, why 1000 volts? Currently, electric vehicle batteries go only up to 400 volts maximum. But there's been talk in the industry and very recently that they're going to go up to 800 volts. So it would be more like 950 volt nominal. So we are already prepared for the up and coming next 4 to 5 years with the advent of battery charging voltage changing to up to 1000 volts. So this charger can actually give you that. The challenges we see is that we do have the challenges on size of the magnetics on the circuit. So it's a circuit board. As you can imagine, the magnetics play the most vital role, that is the inductor circuits on the DC-DC converters, play the biggest, or pose the biggest challenge. The input power quality, which is, we need to keep the supply side as clean as possible to maintain good power input so that we don't pay larger electricity bills. And finally, efficiency targets are of close to 99%. Right now, we get about 95%. The optimal solution would be the variable DC link voltage inside the power converter. So we're working on those. Right now, it stands at about a TRL6. As you can see, this is the product in the picture, in the inset. You can see that the inductors that I talked about, the magnetics, play a vital role in cost. and also reducing power density. Our aim is to increase the power density and go to planar magnetics to replace these transformers. And that's the next version of this power converter. That's the transformer, which also plays a vital role in making it heavier and a little bit more costlier. So yeah, like I said, a US patent has been granted. So our next step is more to so that the charger looks like this, which is competitive with the market chargers, but at variable voltage. Obviously, this charger more than likely is fixed at a certain voltage output. So the patent was granted most recently. It was, the priority date was August 3rd, 2018, as I had mentioned earlier. The efficiency currently sits at 95%. Output over input efficiency, and finally this needs to go up to 99% to be largely competitive. The idea is to make it more compact and more power dense, so by eliminating things like the transformer, going to planar inductors to eliminate the inductors on board, or at least the size of the inductors and the losses associated with that. That will get us to this target efficiency and reduce cost quite a bit. The team consists, currently we have 12 researchers in our group here at Ontario Tech University. We do have 3 full-time lab technicians in building the technology, along with the graduate students and postdoctoral fellows. We already have published close to 50 papers, journal and conference articles, in addition to the patent, as I mentioned. So most of our expertise lies in battery technology, power electronics, and EV charging expertise. We are looking to tailor this technology, as I mentioned, to a particular industry, which would be the electrification industry of mobile devices. So mobility of any sort, not just road vehicles, but also it could be golf carts, it could be aircrafts, it could be anything electrified with a wide range of voltage requirements. And finally, in order to do this work, we would need access to EVs for the purpose of testing and validation. So actually EVs. The other thing obviously would be engineers, lab space, and some testing equipment in order to take this from a TRL5 to a market-ready product. So yeah, in terms of contacts, you can contact me at any time. That's my email address and my phone number. Ala, who's online as well, who's our IP officer from the Office of Research Services, is here. And of course, that's his email address. So thank you for listening, and I'll take questions if there are any.